Welcome learners. We are in module 2 in week 1. In this module we are going to discuss the topic what is algorithm. Before that, let us revisit what are the points we have discussed in our last module. We have seen computer is extremely fast in calculation and capable of storing huge amount of data. And we also said computer can solve only the computationally solvable problems, and then we raised a question what then computation means, and the term computation will provide us the notion of algorithm. Now let us start with the question what computation means. Now to understand this question, let us first take a very easy very simple problem like find out the square root of a positive number n. Now equivalently what we can say that we need to find out the number x such that x into x will become equal to n, because if x satisfies this equation then we can say x is square root of n. Now let's solve this problem. So whenever we have a problem in our hand and we don't know how to proceed, one of the very famous approach is take a particular example and then try to find out the strategy or steps to solve that problem. Once that is finalized, then you generalize your solution method for any arbitrary problem. Exactly in the similar way, let's assume that n is 20, and now we will solve this problem for n equals to 20, and we will find certain strategy and steps. Once everything is okay, then we generalize our solution for an arbitrary positive number n. Okay, so you can solve this type of problem in different ways. I will actually show you two different ways and we will compare them at the end of this lecture, right? So first approach 1, and this approach is basically known as check and guess approach. You know so the check and guess approach is very simple approach, and it is a very useful approach in any kind of computation. So I am giving you the idea how check and guess method work. It is very simple. The idea is we need to find out the x which will give you the correct value of root over 20, right? This is what we want. We don't know the value. So let's first assume x equals to any arbitrary real number x0, starting from minus infinity to plus infinity. Now it's a random choice and random guess. Then now how to determine whether this x0 is the correct answer or not? You simply calculate x0 square. If this is equals to 20, then we will say stop the process as we have received our answer. But since x0 is a random number, arbitrarily chosen number, so most of the time you will get something which is not the root over actual value of root 20. So most of the cases we will get that x0 square is not equals to 20. Okay. Now the point is, if it is not equals to 20, then what we will do? We will now update the value of x with a newer value x1, and we will hope this will provide a little better solution or a good better solution than the previous one. So how do you check whether this x1 is a solution or not? Again, you will do x1 square. If it is equals to 20, you will stop the process and say x1 is the answer. If not, then you will re-update the value of x by x2, and again you calculate x2 square here. Now if it is equals to 20, you will stop, otherwise you will re-update the x by x3. So it is what the process is: guess a value of x, then check whether your guess is correct or not. Therefore the method is called check and guess. Now if your guess is correct, you stop, otherwise you update your guess with a new value and then again check. So these the things we will keep on doing continuously unless we receive our final answer. Now few things are very important. Art of this solution design is standing upon on the updation part, because how you are updating this x, based on that you actually will get your answer. So it's not that every time you are taking some random value. No, there must be certain rule to update this value, then only it will actually reach to the accurate answer. Now let's do little more analysis and then I will come back here. Now what I am saying at the beginning, let's say what is the error x0 minus a. What is a? I am assuming a is the actual root. That means the actual value of root 20. So the actual value of root 20 is nothing but a. I don't know that, but I am just writing a symbol. So at the very beginning, this is what my error was, right? x0 minus a. Because the initial approximation I have considered x0 and the actual is a. So the difference between the actual and my approximate guess is this much. Now if I need to continue, then the next iteration I will update the value of x by x1. So in the next iteration, the difference of actual answer and my guess is this. So I will tell that this is the E0 error. That means this quantity is error in 0th iteration or at the beginning. This quantity is the error at the first one iteration. Similarly, I can still have x2 minus a, that is the E2, and so on, right? Now one thing in this way, let's say I have xn minus a, this is what my nth iteration error. These are all iteration. Every time when you are updating this value, so that means we are going into the new iteration. Now if you notice properly, then if let's say by some way we are updating this x0, x1, x2 so that this value is greater than this one and this value is greater than, that means E0 is greater than E1, E1 is greater than E2, and E2 is greater than E3, and En minus 1 is greater than En. What does it mean? This sequence is a monotonically decreasing sequence, right? So if it is a monotonically decreasing sequence, then of course it will converge into a limit 0, because every time it is getting decreased. So therefore when n tends to infinity, we can say that xn minus a, this will be equals to 0 when limit n tends to infinity, right? So the moment it will happen, then in that case we can write that xn equals to a. That means we will receive our actual answer in nth iteration. Now n may be very large. Ideally it could go up to infinity as well, right? Now, so therefore you need to devise the updation method in such a way so that this decreasing, monotonically decreasing series actually we will able to create, right? So therefore every art and every complexity of this process is lying on the updation process. So now let's do one thing. We take an example and see how it works. In iteration 1 we are the value of x is equals to 5. That's what we have seen. Now since this value 5 is in region R1, which satisfies x into x is greater than n, now in the next iteration we need to reduce this value, and so that we can go closer to the actual root, right? So if we are in region R1, then we need to start reducing that value by amount, certain amount. Now after that reduction, let's say we are still in the same region, then we will do further reduction, right? And we will keep on doing this reduction until and unless we reach to the region R2. Why? Because once we reach to R2, this particular value of x is already less than your actual root, so there is no point of reducing it further, because then we will go far from the actual root. Now we need to change the direction of our movement and we need to increase, right? Again, in the similar fashion, we will increase this value up to how much? When we reach to the R1 region, we will stop that process of increasing, stop this increasing process. Instead, we stop there, and since now here we are already greater than the actual root, we will again start reduce it in forward direction, right? So this kind of alternative decrement and increment is needed to go to the closure of the actual root, right? Now let's write these steps in more detailed way. So this is what I am writing. If x into x is greater than n, that means I am here, then reduce x by d until and unless this x into x is less than n. That means we are in the R2 zone. From R1 we start reducing it, and once we first time reach to the R2 zone, we stop that and then we will change the direction. So now what is this d? Now here at the time of reducing the value, we are actually using this formula x, let's say x equals to x minus d, right? So what is this? The new value of updated value of x will be older value of x minus d. So here x1 is equals to, that means x0 minus d, d0. Now what is the value of d? Initially I will choose the value of d as 1. Okay, you can choose any other arbitrary value. I have chosen here 1. Okay, so therefore what is the value of x1 here? x0 minus d0, which is equals to 5 minus 1, that is equals to 4. Now if we draw this, then the point in the next iteration 2, the point moves to 4, right? Now see here the interesting part. Now after reducing it only for once, I reach to the other side. Now if you calculate 4 square, it will be less than 20. So therefore this point is residing in this region R2. So there is no further decrement is needed or reduction is needed. Now you need to increase it, okay, towards the direction of your actual root, right? Now therefore in step 4, what I am writing is, if x into x is less than n, let's say I am here, increase the x by d until x into x is greater than n. So again I will keep on increasing this until and unless I reach to the region R1. Now here is the important thing. Then what is the value of d here? I understand the value of d here is 1, because we have seen that the value of d0 equals to 1. This d0, using this d0, we actually got this result x1, which is equals to x0 minus d0, that is 5 minus 1 equals to 4. Now when I will calculate x2, this will become x1 plus some d, right? I am writing, for the time being I am writing some d, okay? I will tell you what's the value of this d is. Now one thing is for sure, if you choose a d here, if you choose the value of d is 1, which you have chosen for previous movement, okay, this is my previous movement, for this movement I have chosen 1. Now let's say here as well, while calculating the next iteration, next value of x, so you are increasing by the same amount d, then it will become what? 4. x1 is 4 plus 1, which is 5. See, now x2 becomes 5. We have already seen x0 was 5. Now in the further, after doing further improvement, we actually again we are not getting a better value. We are again coming back to the same older value 5. Why? Because how do you get this x1? by reducing 1 from 5. Then at the time of increase, if you increase by the same amount, you will get back to the same older position. So please remember, while you increase this value, this increment must be less than equal to the decrement that you used in the previous iteration. Okay, so therefore what the rule that I have chosen, update rule, di is equals to 10% of the older di. This 10% is not very important. You can choose for this matter any other percentage as long as that is less than 100%. You can choose 50%, you can choose 40%, you can choose 99%, but it should not be 100%. That means the same di. So therefore here I will use d1, which is 1 by 10 into d0. That means this should be 0.1. So at the time of increment from this place, I will use this formula. x2 is equals to x1 plus d1, which is x1 is 4 plus 0.1, that is equals to 4.1. So if we proceed, will in iteration 3, I am in 4.1. Now you need to improve or you need to increase it further, right? So here you can use the same d, that means the 0.1 which just now we have used, right? We need to update the value of d when we shift the zone. Right now we are still in the same zone. x2 is this and this one is x3. We are still in the same zone, so we can use the same d at the time of increasing these values. But whenever we change the zone and then we need to shift the movement, we need to update the d by this formula. So I will use the same d. So what will happen? Your x4 then will be, this is your x3, your x4 will be x3 plus your d. And what is your x3? x3 is 4.1 plus 0.1, because I will use the same d, right? Because I am in the same zone. So therefore 4.2. So next time we will move further. Here it is 4.2. This is the fourth iteration. So this is x4. Right, now you keep on doing the same thing. After further few iteration, this is x5, this is x6, and this is x7. Now see this x7, this is in the other side of the other region. So here we are, the value of x is greater than the actual root. Now you need to shift your movement, the direction of the movement you need to shift, right? You need to change. So now you need to decrease it. Now how do you decrease? You will use the same formula, x minus d. Now in this case your d2 will be 1 by 10 into d1. And what is your d1? In this entire phase the d1 is actually 0.1, so your d2 will become 0.01, right? So please remember, you need to change your d when the moment you shift the movement direction, that means from decreasing to increasing or increasing to decreasing, you need to change your d so that you should not come back to you should not go back to your original previous position. I hope you have understood this concept. So therefore next time your amount of decrement will be only 0.01. So now step 5, we actually do this alternative movement again and again until and unless we reach to the actual root. So repeat step 2 and step 2 to 4, reducing d by a factor 1 by 10. When you will reduce this? When you shift your movement. If you are not shifting your movement, like this case, okay, you should not change your d, because the same d could be used. Okay, now so again I need to decrease it by 0.01, keep on decreasing. Eventually it is actually coming very close to your actual root, which is 4.472. so we will actually get the final result. So in this case, after 12 iteration, the x value converges to actual root m. Now see one more interesting topic. Now this is what my x1, right? This is what x1, this is x2, this is x3, this is x4, and let's say x5 and so on. Now what is this distance? This distance is nothing but x1 minus the original value, so error. So x1 minus a, if you take the modulus of this distance, this is what x1 minus a. That means it is e1. This distance is the error in second iteration, right? Now what is this? This distance is e2. That is the error in third iteration. And this is e3. This is e4. Now if you notice properly that this error is a monotonically decreasing sequence. So eventually this error will become 0 in the limit. So when it becomes 0, so the moment this becomes 0, we will get our actual answer as a guess. So we will stop our algorithm. So this is what the mathematical analysis, what we have earlier discussed, we are seeing that the same thing is happening here. In all reality, the errors are getting slowly, errors are decreasing, and it will eventually become 0. If you see here as well, this error and this error, this error is less than the previous, and this is even lesser than the previous. So we are going into the right direction. So see the importance of this update rule. This update rule, you need to update in such a way so that it will go close to the actual root. So in this entire check and guess method, the only art is the updation strategy. That's what it is moving into proper direction. And one more final point is that this initial value, if you choose something very big, let's say 5,000, what will happen? The computation method will still be correct. What will happen? It will need some more iteration, because if you start from 5,000, every time you will reduce by 1 and 1, so it will become 4999, then 4998. So anyway, one point of time it will definitely come below to your actual root, because every time you are reducing it, and then you need to again increase it. So as far as the correctness is concerned, if you choose any other large value, it will still give you the accurate answer. But only thing is that it may need lots of additional iteration. In the same way, if you choose your DI, a different formula, instead of 1 by 10, if you choose anything which is less than 1, even 9 by 10, the same rule applies. It will actually go to the right direction, but maybe it may take little bit of extra amount of time or extra iterations. So as far as the correctness of this computation, that will still be correct, but only thing, it may take additional time. So you need to be very careful, and you need to understand each and every parameter, right? But for all these things, there is no problem. Only thing is the delay or additional iteration will be needed. Dear learner, so we have now seen how to solve a problem of finding the square root using our approach 1. And just please note down, in this approach we are creating a monotonically decreasing sequence of error, so that eventually it will converge to the actual root. So in this lecture we will not discuss anything more. In the next lecture we will continue the session on approach 2, which is again very interesting method for solving the same problem. Okay, thank you.